Hello and welcome to this BBC Microbit V2 webinar. So we'll be going through 3 fun projects to show what this new BBC Microbit V2 can do. So with me today, we have myself, Bjorn Kvale. I'm a product marketing engineer at Nordic Semiconductor. And with me today, I'm proud to hand the stage over to Jonny Austin, CTO of Microbit Foundation, very soon.
Thanks very much.
Jonny, if you could go to the next slide, please. Perfect. So just some practicalities before we start. The duration of the webinar will be approximately 50 to 60 minutes. Questions are encouraged. Please type these in the top right corner, not in the chat. The questions are anonymous, but try to keep them relevant to the topic, so not too specific if possible. We'll answer the questions towards the end, so last 10 to 15 minutes. The chat is not anonymous and it should not be used for questions. If you do have any more questions after the webinar, you can always go to Nordic DevZone. That's devzone.nordicsemi.com for Nordic related questions, or you can go to support.microbit.org for help with the BBC Microbit V2. And a recording of the webinar will be available with the presentation in PDF format at webinars.nordicsemi.com/on-demand. You should be able to see that in the chat. So without further ado, I'll hand it over to Jonny.
Great, thanks very much, Bjorn. So I don't know how many of you would have seen the previous webinar that was advertised as part of this. I'm going to just start with a little bit of an introduction to the Microbit Educational Foundation and the Microbit device before doing 3 examples, about 15 minutes per example. And we're going to go at a pace, hopefully, that allows someone who has got a microbit to kind of follow along mostly, but I want to get quite a lot in the 15 minutes. So this is going to be recorded. You can go back and see the content if you want. So I want to talk about who the foundation, the Microbit Educational Foundation, are and what we do. Our mission is to inspire every child to create their best digital future. And this is what the microbit is all about. So we're going to talk about the microbit device. So the BBC Microbit is a versatile programmable IoT device that's designed for use in the classroom. It was designed by a very large number of partners with education as its primary goal. So because of that, it's easy to program. You don't need to install anything to program it or any drivers. It has very simple wireless communication, which is the result of the Nordic chip being on board. It's battery powered. It's got built-in motion sensors. It's instantly interactive, and it's got hundreds of sensors and accessories. So we say it's got a very low floor, very easy to get started, a very high ceiling. You don't need to move away from the microbit in order to go and do more advanced things. You can program it in C++. You can use Zephyr. There are lots of other ways to program the device other than just the education-focused methods that I'm going to show you today. And it's extremely low cost. So it's available in about 70 countries around the world for £10 if you're buying in volume. For say, a government, you're buying lots to roll out into your school, something like that. And it was designed by a coalition of 29 different partners, led by the BBC, with ARM involved. That's the organization that I worked for when I started getting involved in the microbit, and Nordic Semiconductor as well. So that's the kind of fundamentals of what the microbit is. There are now 5 million of them, more than 5 million, in different places around the world in education, helping children get creative and learn about code. So I'm just going to switch cameras so that you can see some microbits I've got on my desk here. So that you should be looking at 3 different microbits on my desk alongside my slides here now, so Bjorn can switch between those as necessary. So this is the microbit. We like to compare it to a mobile phone. It doesn't look very much like a mobile phone, but I think from an educational point of view, one of the things that's made the microbit so successful is how this extremely simple device can help children understand the concepts of a very complicated piece of technology that has a huge impact on their lives. And I think by helping them map the kind of key technological blocks to things that they really understand, it helps them see and kind of engage with the technology, because they go, oh, now I know how my phone works. And if we just take an example, the simple 5x5 LED matrix, by having something that is very simple, you can literally see each pixel, you can see them being turned on and off, and they're under your control. You gain an understanding of what a display is, but without all of the complexity that comes with RGB, with subpixels, with all that kind of stuff. So we're helping kids kind of feel like they've got an ownership of the technology in their lives by understanding something which is much simpler. It's got these 2 push buttons. It's got some touch input and output pins, external power supply source, which they've got holes for banana plugs or crocodile clips if you want to use them in the classroom, and this edge connector down the bottom. But then on the back of the board, so if I flip we've got a microbit V1 and a microbit V2 here. I'll talk a little bit more about the difference in a moment, but that's the back on the camera. If we look at what's on the back of the board now on the slides, so micro USB for power and programming, a reset button, battery connector, and it's got this main processor, which on microbit V1 was an NRF 51822, and on microbit V2 is a 52833. So it's not quite just adding 1 to all the numbers, but it's pretty close. And that processor is where all of the students' code runs. So everything we do today, the code will be running on that Nordic processor. And because of that, we've got this Bluetooth and a custom 2.4 gigahertz radio antenna that allows us to do communication between microbits and microbit and mobile phones. To help it be instantly interactive, there's a motion sensor, or 2 motion sensors, magnetometer and accelerometer. Those are combined into a single chip on later versions of the microbit. And then a really key part of the technology is this interface processor. And this is what makes the microbit special in many ways. This is, when you plug the microbit in, it looks like a USB drive, and that's all managed by this interface processor. It gives you the simple drag and drop programming, the debugging, and some other features that we're bringing to the microbit later in the year as well. I've mentioned, I think, this edge connector idea. So this is a kind of PCB mountable connector socket, which the microbit can slot into, and it does enable a really wide range of accessories. There are more than 200 different accessories for the microbit now, and most of them use this edge connector format, and it can just slot in, and it means there's no kind of confusion about which breadboard holes you're plugging into. Things just work in a really reliable way. So the edge connector has been a really popular part of the microbit. So I think I mentioned earlier, the microbit is a USB drive, and this is one of the key parts of the programming model and one of the things that really helps people get going quickly with the device. So when you plug the microbit into your computer, it shows up as a mass storage device. And that means that you can drag and drop your code that was created in the web browser straight onto the microbit drive, and it will program the microbit, whether that's a microbit V1 or a microbit V2. So that's the programming model, and we'll cover that when I do my first example. And then we have these 2 web-based editors that are our primary editors for coding the microbit: Microsoft MakeCode and the Python editor. So these 2 are the kind of major, most popular and supported editors. But there are also a host of third-party editors that have been built by people in the microbit community that help program the microbit in a range of very different ways. Kodu, for example, is using the microbit as a game controller for virtual worlds. Mu is an offline, locally installable Python editor. EduBlocks is a block-based Python editor. So, and Scratch is very popular, as I think many of you would have used it before, another programming model. So there's this, not only have we got the microbit primary editors, but we've got a huge community of people doing creative and interesting things with the device as well. So that sort of was mainly about microbit V1, and today we're going to be talking about microbit V2. So these slides talk about the new microbit and what's different. So we get to play a bit of spot the difference. So the first difference is this touch-sensitive logo. It's actually capacitive touch. We wanted to help. Firstly, we wanted another button because that's 50% more button. But we also wanted to be able to talk about the kinds of touch sensing on a mobile phone display. So being able to have a touch-sensitive logo is really positive. We've got a microphone activity indicator, which lights up when the microphone is operating. So this is a really important part about being able to have conversations with students about privacy, what it means to have a device in the classroom that can record and respond to audio. And then we've put these notches on the edge connector so that they are easier to connect crocodile clips and other things up to. On the back, you can see we've got a power indicator. So we've actually got a range of power states that the microbit V2 can be in that allows us to do some long-running data logging tasks without running out of battery and some very low-power stuff. We've got a microphone, and we've got a speaker. And it's important to note that the speaker and microphone applications on the microbit V2 are significantly enabled by the extra processing power of the NRF 2833. Got to get the numbers right. One of the reasons we moved to that new processor was so that we could do a lot more with kind of speech and audio processing and generating interesting sounds. So I think it's good time now for me to switch to my browser and show you what I've been talking about. Was that kind of fairly interactive at speed for everybody? It kind of, earlier when I did this, my slides weren't advancing very quickly, so hopefully you're not too far behind.
Should be fine.
Great. Okay, so I'm going to create a new project. So this is the Microsoft MakeCode editor, makecode.microbit.org. I'm going to create a new project, and the project is going to be called Nordic Demo. So when you start a project from scratch, you get a blank canvas, and we'll see in a moment the kind of layout of the MakeCode editor. So on the right here, this is our program. This is our code. This is where we put the blocks and the key bits of kind of program that we want to execute. Then in the middle, we've got what we call the toolbox. So these are all of the kind of API calls that you can make on the microbit presented as blocks. So these are, you can drag and drop these out onto the canvas to do things. And then on the left, we've got the microbit simulator. So this is a virtual microbit that allows you to test your program before you deploy it to the real microbit. And the microbit programming model is really event-based. So it works on these kind of what we call event blocks. So we can do something on start, we could do something forever. We're not going to use the forever block as part of this program. So I'm going to start by grabbing a simple on button A pressed block. We're going to do something on start and something when button A is pressed. So we're going to use this show icon block quite a lot in this example. So we can say on start show icon, and we'll start with a sleepy face. And then when button A is pressed, we're going to show a happy icon. Where's my happy icon? And I'm going to duplicate this now here. And I'm going to change the button. So when button B is pressed, we are going to show a sad icon. So this is a really simple program, 6 blocks. And I can test it on the simulator as well. I can push button A, I can see the happy face. I can push button B, I can see a sad face. So that's your basic getting started. And if I download this now, when I click the download button, that prepares my program. It's not actually compiling it, but it's preparing the program plus the runtime to put onto the microbit. And if I click show in Finder, I've got this file now, and I can drag, just in case that's in case you haven't seen, I've got my Finder window now, so letting things catch up. If I drag and drop this program onto the microbit drive, you can see the microbit itself, the LED on the back is flashing to tell us that the code is being transferred. If I turn the microbit over, you'll see that once the program has flashed, the program starts running. So if we are looking at the microbits now, I can push button A, I can push button B. So far, so simple, but this program would work perfectly well on a microbit V1. And actually, really what we want to look at is some of the features of microbit V2. So we're going to extend this now to show some of the V2 features. And we're going to use these playful sounds that we've built for the microbit. So I'm going to grab this play sound until done block. And the first sound I want to play is going to be a yawn. And we actually worked with a sound designer to help us get these sounds creative, playful. We looked at the examples we could find of people that had built kind of either characters that you had an emotional connection with that still had a very limited set of sounds. So children's TV programs like something called the Clangers, robots like R2-D2, they all have a very limited sound palette, but still a kind of emotional connection that people can make to them. So that's what we were aiming for with these sounds here. So if I duplicate this block, play sound yawn, and then we'll do a happy sound, and then we'll also duplicate this, and then we're going to have a sad sound when something sad happens. So those are going to be the simple examples. I'm going to mute my simulator, and this time, rather than doing the drag and drop step like I did the first time round, I'm going to use a feature of the microbit called Web USB. So this is something that's in MakeCode and the Python editor. And it's a way to get one-click downloads. So that kind of switching between our window, dragging and dropping, it's a really valuable process because it's straightforward. It will work on any computer. But if you've got users with Chrome, or if you've got Chrome yourself, you can do this process of pairing your device over USB. So if I select BBC Microbit, same as that, hit connect. Now the icon here has changed to be a little USB icon rather than a download icon. And I can now, when I click download, it's going to transfer my program directly from the browser onto the microbit. I don't have to switch between the windows to do anything. And the way we'll know that it's finished working, the screen will go blank, and then when the program's finished updating, we'll hear a yawn sound. So you hear the yawn sound. If I push button A, you should see happy and hear a happy sound. If I push button B, we're going to hear a sad sound. Oh, poor microbit. So those are our, very, very simple sounds, and you can play around a lot with these, but they help people build kind of character and emotion into their robots or creations with microbit.
Jonny, just a quick question.
Yeah. So
I'm showing the webcam now. Can you just explain to people which one is the V2 and which one is the V1?
Oh yeah, sure. So the one in the middle that I've been working with is the microbit V2. The one here, the one with the blue one, you can see the difference in the colors, is a microbit V1. So you can see it doesn't have the gold touch sensitive face, and it doesn't have the notches in the edge connector. If I flip them over, you can see that they're very different. We've got the speaker on the microbit V2, and the antenna is much more visible, although they both have antennae. Okay, so this was running on the V2 all along, and I think that kind of helps also demonstrate that what we've been working on for microbit is to make sure, let's make it happy again, is to make sure that programs, there's a very, very smooth transition from the microbit V1 to the microbit V2. And in my next demo, actually, I'll make that even clearer. So far we've looked at the kind of sound output, but we've got two new sources of input on the microbit V2. We've got the logo touch. So if I choose on logo, and we've also got sound. So we've got sound level, so we can do things when loud sounds happen. So if I just grab an on loud sound block and an on logo press block, let's do the on loud sound first. So with a loud sound, we can let us show a shocked face. And we won't play a sound, because what that tends to do is trigger a loop of forever louds, because microbit plays its sound, which is obviously very close to the microphone, and so here's a loud sound and it plays a loud sound again. So we don't want to get stuck in a loud loop, so we won't play a sound in this case. It is worth saying you can set the threshold here for what a loud sound is if you want to control that, but we don't need to do that now. Okay, so on loud sound, show an icon, we'll update our program again, and this time I'm going to clap at my microbit to make a loud sound, and we should see a surprised icon once that happens. So our program should start again in a moment. There we go. Oh, I only needed to talk. Oh, actually, it's not. It's the loop I talked about. It's my yawn sound was the thing that made it scared and loud, and that made it scared and loud again. So it's getting shocked by itself. So let's remove the loud sound one and come back to some sound stuff. And instead, we're going to look at what happens on logo touch pressed. So we've actually got a range of different ways we can interact with the logo. And this maps directly onto the options you've got when you're working with touch, say on a touch screen. You've got pressed, which is a press and a release. You've got touched, which is when the finger goes down, released when the finger comes up, and a long press is when you push and hold and then release. So we're going to do something when the logo is touched. So we're going to take a while loop. And we're going to use the other, this is an event, but we can also get the input of this not as an event, but as a Boolean value, whether the logo is pressed or not. So we can say on logo touched, start a loop while the logo is pressed. And then we're going to use this useful display bar graph option, plot bar graph. Put that in here, just move up a bit. Plot bar graph of, and we're going to find the sound level input block. So here's sound level, plot bar graph of sound level up to, and then sound level goes up to 255. And one of the ways we can know that is that the simulator itself, once we start doing things with sound, if we click on this logo, once we start doing things with sound, we get this sort of interesting sound bar that shows us the current sound level. But what we need to do, if we actually want to update our sound level, we're in too tight a loop, so we need to put in a little pause after we've done that, which gives the microbit time to read the next sound level. So we've got some cooperative scheduling on the microbit, and if you don't have a little bit of a pause, then actually we'll make that more like 10 milliseconds. If you have a little bit of a pause, then the other processes that need to do things like collect sound values can't run. So now we can try changing the sound level, but I'm not touching the logo, so it's not changing at the moment. So let's download this to our microbit, and you can see both the use of both the logo touch and the sound input, if I've got my program right. So we'll debug it live if it doesn't work. Okay, so the program's restarted. And if I now touch this logo, you can see as I talk now, while I've got my finger on the logo, it's doing a live bar graph of how much sound. If I go very loud, it goes very loud. Very quietly, it's very quiet. And once I release my finger, it's going to stop updating the screen. So if I just go quite loud and then stop, then it leaves it on the last signal that we had. So that's a kind of simple walk through all of the major new features on the microbit v2 in a single program. What we're going to do next is have a look a little bit more at how the microbit v1 and the microbit v2 still work together, and actually just also show off that radio feature. So we're going to create a chuck a duck program. So this is going to be a teleporting duck, and we're going to use two microbits, one microbit v1 and one microbit v2 for this, and we're going to use a battery pack. So I'm going to line those things up, and we are going to make a program that teleports a duck from one microbit to the other when you shake the microbit that currently has the duck. So let's start with a shake block. So we always need our events. So on shake. And then we're also going to need a way to create a duck. So we're going to use the on button A pressed as a way to create a duck. And then we're going to have a look at these radio blocks. So we've got group, and the way the microbit radio works is it's a very simple broadcast radio protocol. And every microbit that's in the same group as each other receives every message that's sent on the radio, unless two people are trying to send at the same time, in which case we don't know who's going to receive which message. It's unpredictable. So it's a kind of lossy broadcast protocol, which works really well because it's extremely straightforward. So we're going to start by setting a radio group. We'll set group 1 for now. And then when we shake the microbit, we're going to send a message. That's going to be how we know that the duck has been teleported. So we're going to send a string, and we're not actually going to check what the string is for now, but we're going to send the string duck just to help make the program clear. And then we're going to create a new event block for when we receive the string. So when we receive the string on radio receive string, then we're going to show a duck on our screen. So we're going to use this icon. Actually, I'm going to draw my duck so you can see how we do drawing. So if I take the show LEDs block, this lets me draw a little picture. So if I draw a picture of a duck, let's see what a duck looks like. Maybe a duck looks a bit like that. Maybe it's got a little tail. No, I think a duck looks a bit like that. Maybe more like that. I think that's a duck. So we're going to show the duck on the screen. So at the moment, if we receive a radio message, we're going to show a duck, but we don't ever clear the duck away. So we've actually currently made a duck creator. So what we need to do next is clear the screen. So if we send duck to somebody else, we're going to clear our screen so we don't have the duck anymore. And the last thing that remains to be done is to have a way to create a duck at the beginning of the process. So we're going to create the duck on button A. So the nice thing about this is I can test this, even though it's using radio, I can test this in the simulator before I start putting it on my microbit. So if I click the shake button, that's going to simulate the radio traffic and create a second microbit. So if I now push A to create a duck, and then shake the first microbit that's got the duck, it teleports the duck to the second microbit. If I shake the second microbit, it teleports the duck back. So all that remains to be done now is to put this on our 2 microbits. So I'll start with the web USB download to my first microbit. And that should put the duck program on. And then what we're going to do for the microbit v1, you can use web USB for the microbit v1, but I'm going to show you the drag and drop because I want to talk a little bit about the kind of hex files, the way we're doing hex files on microbit v2 and microbit v1. So our download is completed. We can check it's working by pushing A to create a duck. So that's worked. And if I plug this microbit in now and unplug the power, you can see that we're now running on battery with this microbit. So let's leave that there and plug in the microbit v1. So these are both using Nordic processors, different versions, both NRF51 and NRF52 or 52833, and that means that it was extremely easy for us to port our radio implementation between the 2 different versions of the device. So this time, if you notice, because I've plugged in a different microbit that I haven't paired, I've just got this plain download button. So I'm going to click the download button. It's going to download me a program, and we're going to look in our downloads folder for when that arrives. So microbit chuckaduck.hex. And you can see this is quite big for a hex file. For any of you that have used a hex file before, or know that the microbit v2 has 512K of flash, and microbit v1 only has 256. This looks quite big. And what we've actually done is to keep the experience simple, we've put a microbit v1 and a microbit v2 program, both compiled for the different processors, into a single hex file. And when we drag and drop this onto the microbit, I talked earlier about the interface processor that helps create that USB mass storage. The interface processor is selecting which version of the program it should be programming into the Nordic chip based on whether it's a microbit v1 or a microbit v2. So if we switch now, Bjorn, over to the microbits on the desk, hopefully that's programmed the microbit v1 with the same program. And if I shake my microbit v2, we teleport the duck. If I shake my microbit v1, we teleport it back. So shake, 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 shake. And this is one of those really simple pieces of code that doesn't have very many blocks, but it's created something very tangible, very magic, very quickly. And I think that really helps students in the classroom engage with the process of coding. It helps them feel like they're going to be able to do something in the real world, maybe something relevant to them with a game like this. So that is chuckaduck. And now I'm going to move away from MakeCode. I guess it's worth just showing that the MakeCode editor also has a JavaScript mode. So I can switch to JavaScript here. And that's going to take the blocks that I've already written and present them as JavaScript. So I could now edit this JavaScript, and I can even do something called MakeCode Python, which has been introduced recently, which is kind of the MakeCode APIs mapped onto a sort of static version of the Python language. So that's the kind of power of MakeCode, is to be able to do all of those. What we're going to look at now is our microbit MicroPython editor, which is not static. It's a MicroPython interpreter that runs on the device. And you'll see some of the reasons we think that's really powerful. So what we're going to build here is, if we just have a look at the microbit on my desk again, Bjorn, this microbit is listening to me and copying or lip syncing with me. So whatever I'm saying, it's sort of saying the same thing. It's as if it's a mimic. And this can be quite fun if we play some music at it. So I'm going to play a song from my phone now. So on this one, we've programmed it so its eyes actually pop out when it sings its loudest note, like an opera singer. So to understand how this program is built, we're going to build it up from some simpler concepts. So firstly, I'm going to show you the documentation for the microbit and MicroPython. So as is common with text-based languages, it can be really helpful to be looking at a full set of documentation for how the device works and the APIs you need. So we've got these MicroPython documentation, or these documentation web pages. So they give you an introduction to what's going on, how you can work with the microbit. It talks about different parts of the microbit API and how you can use those. For example, input-output pins, playing music, things like that. And including, there's a speech API in MicroPython, which allows you to kind of make the microbit talk. So I'm going to look specifically in the API documentation at images and microphone. So we're going to start with a very simple example. Put it back to microphone so we can find it later. So as is common in Python, we're going to import a module. We're going to import the microbit module. We're going to import everything from the microbit module. And then we're going to create a local variable called lights, and it's going to be an image. And this image is all ones, so just a simple image. And what we actually learn from images is that images in microbit can have digits 0 to 9 for each LED. So that lets you describe the brightness of each pixel of the display. So this image here is just all the pixels very dimly on. And because our microbit here is running MicroPython live, if I connect to the microbit in the same way we did with MakeCode, I'll just close MakeCode so we don't get those interfering, then I can open a serial connection to my microbit, and I can push Control-C. And now I've got a REPL, which means I can type Python commands live. So I can type, for example, lights equals image. So I can sort of test little bits of my code. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Like that, I think. And now I can do display.show, and I can use tab completion here as well. And I can put that on. And this is going to, if you, when I hit return, that's going to show something on the display of the microbit if I've got my string right. So I don't know if you are looking at the microbit. Hopefully you are. If I hit return now, you can see the microbit LEDs have gone on very dimly. The microphone LED, because the microbit is still listing from the previous program, is on brightly. If I just change that image slightly, so I'll make the bottom row 999 and the top, but the middle row 5s maybe. Just for fun, I'll make this row 1, 2, 3, 4, 5. Right. So now let's change lights, and then I can show the lights again. You can see kind of some of the gradient there of the microbit display. So we know now from this that we can show different brightnesses on the display. So we're going to start with a simple kind of what we call a disco lights program. So in this simple program, we were just using the same things I used on the REPL there. If instead of just showing the lights image, we actually multiply this image by some input from the microphone. So we can do microphone dot, and then we've got the sound level function. So we can call microphone dot sound level. And this is going to, if I now flash this to my microbit, this is going to flash the code onto my device. And you can see now, as I talk, it turns on the LEDs in sync with my talking. And if I choose another tune now, I think I like playing New Order to this particular example. So you might notice that this is actually sending values. You know, most of the time the LEDs are either on or off. We don't have much in between. So if we want to know what kind of values we're getting out of sound level, we can use the REPL again. We can open serial. Actually, maybe rather than using the REPL, we use print. So in our program, we can say print microphone dot sound level, like this. And then when we program this, now every time we go around the loop, we're going to print the actual sound level to the REPL. So if I open the serial now, we'll see the values coming out. So most of the time it's 0. But as I talk, we're getting numbers quite a lot higher than the 9, which was the full brightness. We're going all the way up with normal talking. Perhaps there were some 80s there. I don't know how well that's scrolling by on screen for you, but I saw an 80. If I do a clap, we're up to 110. So we might want to scale based on looking at the live numbers there. We might want to scale our output here. Maybe we want to divide it by maybe 3. That might give us a little bit more nuance in our lights. If I flash this now, you'll see we've got some dimness there as I talk. And if I talk really loudly, or if I clap, then it goes brighter. We're probably still never quite getting as bright as we might like, so we could tune that further. But actually, we wanted to make, we didn't want to make this example. This was just a step along the way of understanding maybe our while true loop and refreshing based on the microphone sound level. So actually, instead, what we want to do is I'm going to cheat a little bit, and I've already made a bunch of images for the different faces. So I'm going to grab my images here, and I'm going to paste them into my program. So we've got a load of different images. So we can, if we want, we could have a look at what each one of these is on the REPL, or we could just look at the numbers to find out what's going on here. So this is the one with the eyes popping out. It's got 9, and then a gap between the eyes, and then 9, and then a row of nothing, and then it's got a big wide open mouth. So we can see 9, another row at the bottom, and then just a wide open mouth. Now this one doesn't have the eyes popping out, but it's still got the big wide open mouth. And this one has a slightly less wide open mouth. So if you see here, we've just got zeros at the edge of the corners of the mouth. And if we go down to the quietest image, here we've just got an eye, and a little dot for a mouth. So these are our different images, and you could do these, you could customize these however you like. So now we need to work out which image to show based on how bright the light is. And we created a sound level variable up here. So we're going to use that. So let's start by setting sound level in our loop to be the microphone sound level. We don't want to divide it by anything. Straightforward. And now we're going to start an if statement to work out which which image to show. So we can do if sound level. Well, actually, I've got my sound levels badly up here. I've got sound level with a capital L, so I need to get that right. Sound level. If sound level, and we're going to say if it's greater than 100, because that was our sort of loud clap. And we're going to do display.show, and we're going to use the image loud 7. And you can see that's our local variable there. Great. And then for now, we can just say else display.show loud 1, our quiet image. And if we run this program, hopefully, again, it might have some typos. We can look at my errors later. If I run this program, we've got if you can see my microbit now, most of the time when I'm talking, we just have the dot. But if I clap, I don't know if you're capturing that, but I'll try and clap a lot. Maybe you can see that we get, or if I blow, actually is probably best. You can see we get the loud face when I'm making the most noise. So now all that remains really is to fill in the bits in between. So we can use elif, and then sound level. If it's greater than 80, then we'll play.show loud 6, and loud 6, and it carries on like that. To save you the pain of watching me type it all out, I'm just going to grab the bit that I prepared earlier. This is a bit of a cheat, but I don't think you want to see me type all of that. And now if I program that onto my microbit, you should see that we are back to the Lipsync example that we started with. So boom, 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 boom. And that's our simple microbit hello world program. No, or our simple microbit Lipsync program with MicroPython. I think that brings me to the end of the demos I was going to show. And maybe we can switch to Q&A.